we just motivated the idea of universal hashing, and we saw one naive way to try to implement it that didn't seem to work very well in practice. So now let's see a method that does work well in practice, that is in fact a common way to implement universal hashing using a prime field, and we'll go over what we mean by a prime field. Okay, so let's review that in universal hashing we would like it to be the case that for distinct elements x1 and x2 not equal to each other, and for this function little h that we've drawn from the universal family that we call big H, we want the probability that x1 and x2 map to the same bucket, that the hash value for x1 and x2 are the same, to be upper bounded by 1 over n, the number of distinct, you can think of it as distinct buckets in the hash table, or just basically the range of the hash function. Okay, and so in this universal hashing using a prime field setting, we want to think about this problem actually not just as going directly from u to v, but by way of these hash functions, but we're going to add an intermediate sort of parking zone, a place where we're going to park hash values in the middle, and then we can make some statements about what's going on in that middle space, and then we'll again move from the middle space to the final range of the hash function. So actually the diagram we'll be looking at repeatedly looks like this. Again, we've got our universe on the left, and again we've got the range of the hash function on the right, and the universe we'll say is size m, and the hash function's range is size n. But what we have added in the middle is a new set. Basically this is numbers from 0 up to p minus 1, where p is a prime. So where p is a prime. And the idea is values will make their way from the universe to the range of the hash functions along two sort of hops. There will be one way that we get from u to the prime field, and then another way that we get from the prime field to the range of the hash function. Okay, and you'll see more about why we do this. So let's actually look at what this universal hash family looks like. So I'm going to write a definition of the universal hash family using sort of set builder notation. So I've got big H equals, then I've got little h subscripted with a and b. Okay, in other words, when I go, the members of this family are going to be all the little h's that I can choose by choosing an a and a b, a subscript a and a subscript b. Okay, and a and b themselves, I've written down what those can vary over. So a can vary from 1 to ... up to p minus 1, the prime minus 1. And b can vary from 0, 1 to ... up to the prime minus 1. Okay? So just note, a can't be 0. A can't be 0. Okay? So this not only tells us what are the contents of the set, it also tells us something about how do we draw a hash function from this set. We're going to draw a hash function from the set by picking an a and a b uniformly at random from these sets that they vary over. So we'll pick a random a from here, pick a random b from there uniformly, and we will in that way be able to construct one, we'll be able to sample one hash function from the hash family. Okay. All right, and then so that's we've defined the family, but we haven't said what the hash function actually does, and presumably it's going to do something with this a and this b that are its subscripts. So what is the hash function actually going to do? It's going to do the following. It's going to take the value x, it's going to multiply it by a, and then add b. All right, multiply it by a, and then add b. But we are going to then take the remainder after integer division by p. In other words, we're going to take that value modulo p. So we're going to take the remainder of ax plus b after integer dividing by p. Okay. All right, and that's going to give us a value from 0 up to p minus 1. In other words, that inner set of parentheses is talking about what's happening when we move from here to here. Then, furthermore, we're going to take that result modulo n. In other words, we're going to take that result and take the remainder after integer division by n. And that's going to be the second step. That corresponds to this step here. So this is like the mod p step, and this is like the mod n step. Okay, we'll talk a little bit more about mod and integer, remainder after integer division and modular arithmetic when we get to the prime field part in a moment. We don't really yet know why it's important, for example, that we picked a prime here. Why does this have to be prime? It's a mystery so far, but we'll cover all this. Okay, so let's just think about the way I've defined this set, big H. How many items are in the set? How many hash functions can we possibly draw from the set? Well, that's nothing more than how many different ways can I pick A and B, right? So for A, I have, this is not P ways of picking A because it goes from 1 up to P minus 1. This is just P minus 1 different ways of picking A, all right? So let's say there's P minus 1 ways of picking A. How many ways do I have of picking B? Well, that varies from 0 up to P minus 1, so I have P ways of picking B. So how many members are there? It's P times P minus 1. The P ways of picking B and the P minus 1 ways of picking A. Okay? A question that might be on your mind is, why do we have to do this in 2 steps? What's the purpose of sort of parking these hash values in this prime field in the middle? What is that doing for us? And as you'll see, the answer is it's what's going to allow us to do the analysis that proves the property of universality, that the probability of collision is at most 1 over n. But we haven't seen why yet. So let's start by introducing the idea of a prime field. Okay, so a prime field, and let's, to introduce a little bit of notation, a prime field for a given prime P will denote this way with a sort of bold F subscripted with P. So a prime field using prime P works with the numbers in 0, 1, 2 up to P minus 1. And it defines rules for addition and subtraction of those numbers, right? So these rules will in some ways mimic the usual addition and subtraction, except that we have to do them in a modular way. Like there's a kind of wrapping around, almost like the hands of a clock wrapping around, so that when we do addition and multiplication of 2 of these numbers in this set, we're going to get a third number also in this set, which might mean we have to sort of wrap around. So when we define these addition and multiplication operations on these items, they're going to have some familiar properties, properties that we are familiar with from normal classical algebra using integers and rationals and real numbers. So, for example, let's write down the table for addition in the prime field. So that's this table here. And I won't enumerate all the properties. That would probably take too much time. But I'll just show you that one property that we're pretty used to is commutativity. Right, so a plus b equals b plus a. That's reflected in this table because I could draw a diagonal line like this and you can see that it's symmetric, right? 3, 3, 4, 4, 0, 0. So the fact that this matrix is symmetric is telling us that addition is commutative in the prime field. Now that's just one table. Let's also bring in the multiplication table. So now I've got my addition table, my multiplication table. And as expected, the multiplication table is also symmetric. It's kind of nice because the fact that these are the only numbers we need to worry about, those are the only numbers in this prime field, means that we can write down the finite number of possible addition and multiplication problems in these tables. We're just writing down the answers to all possible addition and multiplication problems involving 2 numbers. So the definitions of addition and multiplication are using modular arithmetic, the kind of arithmetic that wraps around, like a hand on a clock. So for example, let's just focus in on one of the elements. Let's focus in on this element in the addition table, what that's essentially saying is the operands are 3 and 4. So it's saying 3 plus 4, of course, if we use the full set of integers, 3 plus 4 equals 7, but we are actually taking that 7 and then taking its remainder after division by 5, because this is the prime field f sub 5, right? So we're taking 7, the remainder of 7 divided by 5, which is 2. So that's why we have 2 in this element right here, okay? Okay, so let's just do also one of the multiplication table numbers. Let's pick this one. So what this is saying is that, what are the operands? 2 and 4. So this is saying like 2 times 4 we know equals 8, but 8 mod 5, integer, the remainder after integer division by 5 is 3. So that's why we have a 3 here. Okay. All right, so fields have properties like commutativity of addition and commutativity of multiplication and identity elements and associativity and things that you're used to and that you remember from normal classical algebra. But there's something very special that prime fields have that, for example, the integers don't have, which is multiplicative inverses. And that's kind of the key property and the whole reason why prime fields are an important tool here. So fields are special for having so-called multiplicative inverses, by which I mean that each number, 0, 1, 2, 3, 4, in the case of f sub 5 here, has another number, except 0, I should say. So each number except 0, 1, 2, 3, 4 in this case, has another number that it multiplies with to get 1, right, according to this multiplication rule. So for example, let's see. So 2 times 3 equals 3 times 2, right, equals, these both equal 1 after integer division by 5, okay? So 2 times 3 equals 3 times 2 equals 1, right? Obviously, in integers, they would equal 6, but after we take the remainder after division by 5, they equal 1. Okay, so 2's inverse is 3, and 3's inverse is 2. What's the inverse of 4? Well, it's itself, actually, because 4 times 4 is 16, which is 1 modulo 5. Okay, 16 after integer division by 5 has a remainder of 1. And then how about 1? Well, its inverse is itself. That's obviously 1 mod 5. Okay, so every number besides 0 has a multiplicative inverse. Another number, also in the set, 1 up to p minus 1, that it multiplies with to get 1. And you can see that, actually, just by taking this part of the table, right, and seeing that every row has a 1, and every column has a 1. And so that indicates that there is another number that you can multiply. You know, if you're looking at the columns, there's a row that contains a number that you can multiply the column number by in order to get 1. Okay. So, what's so special about primes? Can't we just say that we've got a field? I'm putting a question mark here because it's not clear whether it's really going to have the field properties. We have to sort of assess this. Do we have a field if we were to do integer, remainder after integer division by 6, modulo 6 instead of modulo 7? 6 is not a prime number. So let's see, does it work? Well, let's define the multiplication table that we would like to use, where again, we're doing normal multiplication, but then taking the result modulo 6. And some interesting things are apparent here that weren't the case for the f sub 5 table. So first sign of some sort of trouble here is that we can get zeros. We have these 4 zeros in the table that are not in the first row or column. Multiplication by 0 yields 0. 0 is the nullifier. So these are not so interesting. But these zeros are interesting because they're examples where we multiplied 2 non-zero numbers together and got 0. All right, so we can get zeros by multiplying non-zeros. This was not the case for the f sub 5 multiplication table. So that's one thing that's different and perhaps not so good. And then the second sign that something's different and maybe wrong here is that some rows are missing 1. They have no 1. Some columns are missing 1 too, right? So that means there's no multiplicative, in general, there's no multiplicative inverse, right? There are numbers in this thing that's not really a prime field, like 2, 3, and 4, that have no multiplicative inverse. Okay, so this is the first sign that we really do have to pick a prime in order for this to work. If multiplicative inverse really is important, then we really do have to pick a prime. We can't pick a composite number as the one we use for our modulo. So, okay, given this property of the prime field, specifically the multiplicative inverse property, and the fact that we can, if we multiply two non-zero elements, then we should get another non-zero element, let's start to answer questions about what that might be getting us in terms of this universal hashing strategy. So imagine this. Let's say we choose a distinct x1 and x2, right? This is the case we most want to consider because the distinct x1 and x2 are, the universality property applies for how often we have a collision between two distinct keys, right? So let's say we chose two distinct keys from the universe. Let's ask, can they collide in P? All right, do they ever collide in P? Okay, so that's like asking, right, because our function is just basically, the function that gets us from here to here is just ax, let's do ax sub 1 first, ax sub 1 plus b. And then for x sub 2, we have a x sub 2 plus b. And the question is, can they be equal? Is it possible for a and b, I'm sorry, for x sub 1 and x sub 2 to collide after applying ax plus b modulo p? All of this, I should have written, all of this is mod p. Right? This whole expression is, we're doing everything modulo p. Okay, so let's think about whether this can be true. All right, so let's write it out again. So let's set them equal to each other. Let's hypothesize that it's possible. Okay, so, and this is all mod p. Now let me subtract b from both sides. So I'll have a x sub 1 equals a x sub 2, still mod p, all of that mod p. And then let me gather everything on the left-hand side now. So let me say a times x sub 1 minus x sub 2 equals 0 mod p. Okay? So let's think about what we have here. We are multiplying two things, a, whatever a is, and x sub 1 minus x sub 2, whatever that is. Well, whatever a is, we actually know something about a, which is that it's not equal to 0. Because remember that when we said to pick a hash function from this family, we choose a from 1 up to p minus 1, and b from 0 up to p minus 1. So b can be 0, but a cannot be 0. So one thing we know right away, this is not 0 right here, this a. Okay? Also, x1 and x2 are distinct, right? x1 and x2 are distinct. So x1 minus x2 also can't be 0. So that's also not 0. We said a is greater than or equal to 1. That, in other words, we always choose a to be 1 up to p minus 1. And we said that x sub 1 is not equal to x sub 2. So that left-hand side is the product of two numbers, and neither of them is 0 modulo p. So a is not 0 modulo p, because we can't pick 0. x1 minus x2 is not 0 modulo p. Okay? Because they're distinct elements from the universe, and p is larger than the size of the universe. So it's not possible that they could be, that this could be 0 modulo p. So what we're saying is that if this is possible, then it must be possible that we can multiply two non-zeros and get 0. Is that possible? Well, let's take a look at one of these multiplication tables for a prime field. I'll just pick, to be concrete, I'll just pick 7. And what we notice, so we're multiplying two non-zeros. Okay, so let's take the non-zero part and the non-zero part. And so this is the non-zero times the non-zero part of the table. And are there any zeros in there? No, there's no zeros in here. It's actually not possible in a prime field to multiply two non-zero elements and get back 0. Let's see this in another way. So let's again suppose that it's possible to do this. So if we're saying that there are two elements that are both non-zero and we can multiply them to get 0, that's like saying, let's call these A and C for the purpose of this discussion. These are the non-zeros. So let's say we can take two non-zeros, A and C, and multiply them and get a 0. If we can multiply them and get a 0, that means shifting now out of the prime field but to the integers, that we could just multiply them together and get some number that's a multiple of p. So that's what we're saying here. P is still that prime number. We're not doing modular multiplication here. We're just doing normal integer multiplication, which means the statement that we just made that you can't multiply two non-zeros and get a 0 is like saying you can't multiply two integers A and C and get back some multiplier times p. Okay, where p is prime and z is some integer multiple, A and C are not 0 mod p, right? So is this possible, right? Is this possible? Well, to think about this, let's consider that A and C have, these have prime factorizations. Right? There's some way to factor those two numbers, A and C, as a product of primes, right? All right, and so if this holds, right, there's a p over here and p is prime. So in order for this to hold, it must be that p appears in the prime factorization of A or B. I'm sorry, A or C, or both, right? In other words, for this equality to hold, p has to be one of the things that ends up in the product when we find the prime factorization of A or C, right? But it can't be, because if p were one of the factors appearing in the prime factorization, that would mean that either A or C or both were 0 mod p, right? That's just by definition of what mod p means. If I'm a multiple of p, then once I take modulo p, I become 0. But we said that they are not 0 mod p. So in order for this to be true, that's a contradiction because we said at the outset that A and C were not 0 modulo p. Okay, so this is just another way of saying, no, this is not possible. We can't multiply two non-zeros in our prime field and get back a 0. So all of that was just in service of the argument that we actually cannot experience this. We can't have a situation where we take x1, we take x2, we put them both through ax plus b mod p, and end up on the same spot in the prime field. Not possible. Not possible. Bloop. Distinct items from U will not collide in the prime field. Okay. So if they're distinct to begin with, they're still distinct after we take ax plus b mod p. Let's look at this another way, and actually in a way that's helpful for some future analysis too, which is, let's make a bigger table. We wrote down a table that has the rules for addition and the rules for multiplication, but let's write down a bigger table that's for ax plus b, so the addition and the multiplication together. Okay, so that table will look like this. Right, again, so this table is for ax plus b for the big F sub 5 prime field, right? The prime field modulo 5. And these rows correspond to the input x. These columns correspond to choices for A and B, right? So I've got every possible choice for A and B. Don't forget that A can't be equal to 0, right? So you don't see a equal to 0 anywhere here, because that's not possible. We can only pick a from 1 up to p minus 1. But we can pick b equal to 0, and so here it is here. And in fact, if we think about this block, this chunk of columns, this is the chunk of columns. We're doing ax plus b, but this is the chunk of columns where b is 0. So if b is 0, then you can forget the plus b part. That's just adding 0. So all we really have here is basically 4 columns from the multiplication table copied here. Right? So these are the 4 columns of the multiplication table where we have columns labeled 1, 2, 3, and 4, and then rows labeled 0 up to 4. Okay? So it's obvious how to fill in these first 4 columns of the ax plus b mod p table. I just copy them over from the multiplication table. Okay? So these are purely just copied from the f sub 5 multiplication table. And notice that each column is a permutation of the integers modulo 5, right? So every column has 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. Right? Every column is a permutation of those numbers, 0 up to p minus 1. Okay, so that's just the first 4 columns. Let's think about the next 4 columns. Well, the next 4 columns are going to have a very strong relationship with the first 4 columns because A is 1, 2, 3, 4, just like A was 1, 2, 3, 4 over here. The only difference is that now B is 1, whereas over here B was 0. So what do we have to do to these values to get what we need to put in this rectangle? Well, add 1 modulo p. So we have to add 1 to all these values. It's like a little, and then, you know, if we get 5, we have to wrap around to 0. That's since we're doing it modulo 5. So all I'm going to do to fill this in is, let's just go along the first row. That one's simple. They're all 0s, so I'd have all 1s over here. The next row is 1, 2, 3, 4, so I would have 2, 3, 4, 0, because I have to wrap around. All right, 3, 0, 2, 4, etc. Right, I'm just taking these numbers and adding 1. Okay, same as the block to the left, but plus 1 mod 5. All right, and same argument for the next chunk, right? Again, I've got A equals 1, 2, 3, 4. The difference is that now B equals 2, so I can take the B equals 1 set of columns and just add 1 to everything, modulo 5, etc. So that's how I would fill in this table. We saw that the first 4 columns were all permutations of the numbers 0, 1, 2, 3, 4. Well, the way we constructed the rest of the table means that we preserved that fact, right? If we take a set of columns that are all permutations of 1, 2, 3, 4, and then just take all the values and add 1 modulo 5, I still have permutations. I changed what the particular numbers were, but because I changed every number the same amount, I've shifted every number over by 1 cyclically, I didn't change the fact that all the columns are still permutations. So this whole matrix here, every column is a permutation of the numbers 0, 1, 2, 3, 4. And they're all distinct, right? So they're all distinct permutations of the numbers 0, 1, 2, 3, 4. Okay? And so I'm making a statement here, and I'll reinforce this a bit in a moment. Distinct x's get distinct answers, right? Distinct x's get distinct answers. This table shows us that because every column's a permutation, right? So if I'm in a particular, if I choose a hash function, let's say I choose this one, I chose that hash function. 2 different x's are going to get 2 different values because the column is a permutation, right? So nothing's repeated. Okay. All right, so we just learned something important, which is that the first step of taking ax plus b mod p won't create any collisions. So distinct x's will yield distinct ax plus b mod p's. So now let's think about what's the probability that I get a particular pair of answers for a particular pair of distinct inputs. So I've got these distinct inputs x1 and x2, and I'm going to put them through ax plus b mod p, and I'm going to get distinct, they're definitely going to be distinct, this is what we just argued. I'm going to get distinct values, u and v. I'm going to ask the question, what's the chance that I get a particular u and v? What's the chance that I get a particular u and v? So here I have the expressions for what the ax plus b mod p part of the hash function will do for inputs x sub 1 and x sub 2. Right, so a times x sub 1 plus b mod p equals u. So u is just a variable. It's whatever we get when we do the ax plus b mod p. Same for x sub 2 and v. And we can take these two equations and subtract one from the other and rearrange. And if we do that, we'll end up with particular constraints on a and b. Okay, so here's a. For b, we'll get u minus a x sub 1 mod p. Okay, and the point about these expressions is that there's only one possible choice of a and b that are going to satisfy these equations. So for a given x sub 1 and x sub 2, there's only a particular choice of a and b that are going to yield a given u and v. And I'll show you this in a moment in the form of the table, which is perhaps an easier way to visualize what's happening here. But what it means is that there's only a single choice of a and b satisfying the equations, so the chance that we outlined on the previous slide is just 1 in the number of possible choices of a and b. It's just 1 over p times p minus 1. Right? There's only one choice of a and b that satisfy, therefore the chance of this happening is the chance that we pick that a and b, and that's just 1 in the total number of possible choices. And all those UV pairs are equally likely. Right? They all have this. We yield any given UV pair with this probability. Okay, so let's see how this fact of the single choice of a and b satisfying the equations can also be thought of in terms of the table that we already wrote down for ax plus b mod 5. So let's just arbitrarily pick an x1 and a u and an x2 and a v. And I just picked these kind of arbitrarily. So I've got x1 equal 1, u equal 4, x2 equal 3, v equal 2. Right? So the question we're trying to answer is, for which columns do we observe this combination? For which columns of this matrix do we observe this particular combination? So let's just visually see if we can figure that out. So let's see. So we need x sub 1 to be 1. Right? So we're going to be concerned with this row. And in particular, we're looking for the times when this row equals 4, right? Because the ax plus b mod p is mapping x1 to u. It's mapping 1 to 4. So we're looking for the places where there's a 4 in this row. And likewise, the other row we're looking at is 3. And we're looking for places where that's equal to 2. So we're looking for a 4 in this row and a 2 in this row. So let's see. Okay, I see a 4 here. See a 4 here. See a 4 here. 4. Okay, that's it. Then I'm looking for 2s in this row. 2, 2, 2, 2. And there's only one column in which they coincide, right? This column right here. There's only one column in which they coincide. That's another way of visualizing what we were just saying. Okay? So that happens, that combination happens in exactly 1 out of the p times p minus 1 columns. Okay, so that's interesting because we've just characterized what happens when we take that first step, where we've taken the value from the universe u, we figured out ax plus b mod p, so now we've got a new value that's in the prime field. We know that if the items were distinct to begin with, they'll have distinct slots in the prime field. And we know that the probability that we get a particular pair of slots in the prime field is just 1 over the number of possible choices of hash function, 1 over p times p minus 1. So the last thing we really need to worry about, and in some sense this is the most important part, is when we go from p to n, obviously we're narrowing the number of slots, right? We're going from a large number of slots, p, which is greater than m, greater than or equal to m, down to the range of the hash function, which is presumably, in most situations, much smaller. So we have to analyze the collisions that are going to result from this final step, which is that we simply take the result of ax plus b mod p, and we take that mod n. That's the final step. That's the step that gets us to this range. So this obviously is going to cause collisions. There's no, we're not going to be able to make the same sort of statement we made before where we said if the items are distinct, they won't collide in the prime field. Now we're going from something big to something small. There's no question that there are going to be collisions now. The question is, can we say that they're upper bounded by 1 over n? Because that will give us universality. So let's think about these collisions. So let's start with this simple diagram where I'm considering u, one value from the prime field. It's gonna, after we take mod n, it's gonna map to some element in the range v, right? Let's call that this dot here. And let's think about what are the other elements of the prime field that are going to collide with u. And this is easy, right? Because the operation that's taking us from here to here is simply mod n. So it's u, basically, plus or minus a multiple of n. Right? So let's call this n plus u, and 2n plus u, and minus n plus u, and minus 2n plus u. There's no point there. Those are the ones that are all going to collide here on the same point. They're all going to the same point. Okay, so taking a number u in the prime field, the other numbers in the prime field that will collide with it mod n are plus or minus the multiples of n. Great. So let's visualize this with a matrix that looks like this. So note, first of all, that I picked a particular prime, p equals 11. And so this is an 11 by 11 matrix, and I've numbered it 0 up to 10 here and 0 up to 10 here. And I'm imagining for two distinct x's, for x sub 1 and x sub 2, I got two distinct numbers in the prime field, u and v. And now I want to analyze what are the chances that there's a collision between u and v once we take them mod n. Okay, so I want to fill in this matrix for what it looks like after we take these mod n. And let's note something, which is that because I'm analyzing the situation that start with distinct x's, x sub 1 and x sub 2 not equal to each other, that means that they'll map to distinct items in the prime field. That means u will not be equal to v. So these elements along the diagonal aren't relevant to our analysis. So I'm just going to gray them out. They're not possible. Right? If x1 and x2 are distinct to begin with, then u and v are going to be distinct as well. And now let's just pick, so I picked an arbitrary value for p just so I could make a picture. Let's also pick a value for n. Let's say that n equals 4, right? So I'm going from 11 to 4. Okay. And now I just want to augment this picture by highlighting all the elements that correspond to a collision modulo 4. So that would be these items. Like, for example, why is this item a collision? Well, because u is 0 and v is 4, and those are both 0 mod 4. Why is this item a collision? Because u is 1 and v is 5, and those are both 1 mod 4. All right, so the ones highlighted red are the ones that collide. So what we would like to argue is we'd like to be able to argue that the fraction of non-diagonal items in this matrix that are colored in is upper bounded by 1 over n. That is essentially the universality argument. So let's take a look at that. Let's just look in one row. I think that helps, just to look in this one row. As you can see, each row has for one element in the diagonal, some elements that are white, some elements that are red, indicating collisions. And they're all equally likely, right? We said that any given u and v has probability 1 over p minus 1 times p. All right, so they're all equally likely. And we can write down an analysis that looks like this. We can say at most, ceiling of p over n minus 1 choices are collisions, based on using the in general. And therefore, we can say that the probability of a collision is at most ceiling of p over n minus 1 over p minus 1. That's sort of like considering a particular row of this matrix, which is at most this, which equals 1 over n. Okay? And this argument works. But I think it's a little bit simpler as long as we're looking at a picture to just think about what is the argument in terms of this picture. So let's just sit down here in the first row and walk across from the diagonal and consider what pattern we're seeing. Because the pattern we're seeing is really obvious. We're seeing that every nth item in that row is a collision, right? And it's not quite the case that 1 over n of them are collisions, because after all, there's like a little bit of, there's a couple of non-collisions here on the end, and we don't have enough elements in our matrix to get to the next collision. So you can see that that is clearly upper bounded by 1 over n in a given row, just visually, right? No collision, no collision, no collision, collision. So n minus 1 out of the n were no collision, and then next collision there, etc. And of course, you can make the same argument in any row by going along from one end and going along from the other end, right? There's even a row here that has only one collision, right? Because of sort of a coincidence of where we are in the matrix. Okay, so it was important, though, for us to be able to establish that these are not collisions here on the diagonal. They're not possible. That was an important part of how we ended up being able to argue that it's upper bounded by 1 over n. Being able to argue that all combinations of u and v were equally likely. Those are both things that flowed from the fact that we were using a prime field. So that's why it was very important that we used a prime field, that we had multiplicative inverse so we could make these arguments. And at the end of the day, we get that the probability of collision is upper bounded by 1 over n, which is exactly what we wanted. That's the universality property. So yeah, this family of hash functions where we do ax plus b mod p, inner parentheses, and then mod n, outer parentheses, where a and b are chosen uniformly from either 0 up to p minus 1 or 1 up to p minus 1, that family is universal. Let's see if it satisfies the criteria that we had coming in. We said it should be easy to draw hash functions from the family. It was not so easy in the case of the idea of uniform hashing, where every possible way of assigning items from the universe to items in the range of the hash function, that we said was very difficult to draw from, because we had to make an enormous random map every time we drew a new hash function from that family. Here, it's easy. We just pick a and b. That's all we do. We uniformly pick a from this range and uniformly pick b from this range, and that's it. Then the hash function has this form. So is it easy to draw functions from this family? Yeah, very simple. 2 uniform draws from small sets of numbers. Is it easy to store the hash function? Yep. Once we store a and b and this formula, we have everything we need to run the hash function. And are they easy to compute? Yeah, this is all stuff that modern computers have no trouble doing, right? Just multiplication, addition, and modulus. You know, modulus, since it involves at least a flavor of division, is one of the harder operations for a processor to do, but we're only doing 2 of them. So it's really not a very big deal. And this is a very efficient function to compute with.